dv squared, okay? Plus higher order terms even than that. Now the idea to Newton iteration is that you just keep these two terms and you forget that. So you approximate the IV curve with an IV line. Okay? And then you do this for every single nonlinear element in the whole schematic. Now it might not be obvious how you would make what the IV curve of a transistor is. Well, let me say what's here first. So if you just have this, you have I of 0, this IV line, here you have I0 times this delta V times dIdV. This is a conductivity, and that's a current. So this is actually a Norton equivalent circuit. That's what that is. Okay. The first two terms of a Taylor series comprise a Norton equivalent circuit, and you replace all the nonlinear elements in your whole schematic with Norton equivalent circuits. Now, for a transistor, these aren't conductivities, but transconductivities. Transconductance is basically conductivity at a distance. You know, the coefficient of conductivity, conductivity is the coefficient of current you get between two node voltages, depending on how much voltage you have between them. If you look at the voltage multiplied by the conductivity coefficient, you get the current through that. That's what conductivity is. Transconductivity is the same thing, but at a distance. It's the current between these two nodes for the voltage between these two nodes. That's conductivity. So you replace the whole circuit, every nonlinearity, with Norton equivalent circuits and Norton equivalent trans circuits. Now, if you do that for every single nonlinear in your circuit, you now have a linear circuit, and you can set up a system of equations of GV equals I. See, G and I, these are Norton equivalent circuits. Then you solve for what the voltage would be if this approximation were the correct one. If this voltage is equal to V0, that's it. You found the answer. Newton iteration results in a numerical proof that you found the answer. That's what it does. That's why SPICE can solve arbitrary nonlinear circuits, is because when it's done, it proves it's found the answer. That's why it works. Now, if this solution is not where the point about we expanded, the Norton equivalent, Newton iteration gives a prescription for what new point you should iterate to, what you should use, which basically means if you solved it, say this is a different V, expand about the solution of this voltage vector. And it's blindingly fast because this equation is correct through first order. I mean, if you have this derivative correct, if there's no bugs in your SPICE program, and that actually is the derivative of your curve, this equation is correct through first order, which means this is all second order and higher. So if you're within 10% and you solve that, your next iteration is within 1%. Do it one more time, you're within 10 to the minus 4. Do one more Newton iteration, you're within 10 to the minus 8. So it's just blindingly fast. Okay, it only takes a few Newton iterations to nail the solution. That's what Newton iteration is. Now, all the your SPICE program then, it spends all of its time setting up this matrix and solving that voltage. Setting up that matrix, solving. That's the only thing it's doing. Why that's useful, why that relates to actual solving the circuit is just an argument. But the software doesn't worry about the argument. It just knows it has to solve this, compute this matrix and solve it. Compute the matrix and solve it. That's all the thing. That's the only thing it does. So you can tell how to write a faster program and how you can make it more robust. Now, the thing is, what I just described with Newton iteration, it sounds so different than what we learned in linear algebra class. You know, we all had to take linear algebra class, and we learned about matrices and order and determinants and transpose, and we learned it all, right? Rank, file, order, all that. And when on the last day of class, if your professor was honest, he told you this: look, this is the way it works for a linear system. If you have a non-linear system, we're basically going to wish you a lot of luck with that, okay? So that's so different than this story here that I say, well, it could take it could solve for the solutions blindingly fast. And it's so different. How can both of these perspectives be true on the same planet? Well, it's because Newton iteration exploits the fact that an electronic circuit is not an arbitrary linear system. It's a very specific type of nonlinear system. What's unique about a circuit is that all of the IV curves are continuous in value and slope. They are everywhere differentiable. Okay, and only if your IV curves are everywhere differentiable is even the argument that you've proved you found the solution is even valid. And the method that you need to have all these things, you need to have all these derivatives exactly correct. So that's why both of these things are true in the same. Anyway, you can tell the robustness of one SPICE program on another depending on whether or not the IV curves in the software are continuous in value and slope. The real circuit, they're continuous in value and slope, but there's bugs in SPICE programs, and these IV curves of the devices, transistors and diodes in SPICE are not continuous in value and slope because of these bugs. For example, here's a diode in Berkeley SPICE. That's a discontinuity in the diode. It's just a bug in the program, okay? And it's not in LT SPICE. Now, that's not just in the P, that's just not a diode, that's every PN junction in Berkeley SPICE has that discontinuity. So it's in the diode, it's in the JFET, it's in the bipolar transistor, it's the substrate of a MOSFET. BSIM3 has that discontinuity in it. Okay, so every semiconductor in Berkeley SPICE has at least that discontinuity in it. But there's other examples. This one is not in the paper you have. This is channel length modulation of a MOSFET. The channel length is modulated by the voltage across the drain and source. And eventually, if you punch through, in Berkeley SPICE, it has these discontinuous IV curves where in LT, and it's just a bug in the program. Just a few lines of code are just typed in incorrectly. And so it doesn't have that. There's other examples. Here's the IV curves that are continuous in value but not slope. Anyway, I'm from UC Berkeley. I'm familiar with these bugs. I've fixed all these things. There are no discontinuities in LT SPICE. At least none of them are reported to me. And that's not all of it. You don't have to just make the IV curves continuous in value and slope. There's other types of singularities that come up. Say you want the drain current of a MOSFET. You might say, oh, the drain current is this function divided by that function. But you might have a point where they're both zero. Well, the drain current isn't undefined, but the way you formulate it is undefined. So how do you fix that problem? You apply L'Hopital's rule. You differentiate the numerator and denominator, and you have to trap it, and and you can just deal with this. This is all very basic stuff. LT SPICE has L'Hopital's rule applied in about 50 different places. L'Hopital's rule doesn't occur in Berkeley SPICE. These are the sorts of things you do to make it more robust. Now, for speed, there's a lot of things here. LT SPICE uses multi-threads to solve these G vehicles. I see the speed comes down to the time it takes to compute the matrix and solve the matrix. Those are different things. Computing means solving these G's and these I's and then solving this matrix. The G's and I's, these are all independent. They can be solved in different threads. And then for the I's, I actually use self-authoring code. That is, when you poke the running man, after it's parsed the netlist and put it in data structures, LT SPICE will actually write an assembly language program for that matrix. And by doing that, it can keep the floating point processor pipeline full, because it actually takes more time to get the floating point data to the floating point processor than to actually do the floating point operation. And it has for about on any processor made in the last 20 years. If you write any program in C, the floating point processor is empty. You're just clocking data through an empty clock pipeline. And there's no way to avoid it, no matter how good of code or compiler or even assembly language you have. The problem is that when you call malloc, you don't know the address that came back. And you can't get, and you have to programmatically at runtime find out, compute the address of where this data is, and then get it out of RAM through the traces on the board and into the floating point unit. And that takes many clocks. But if I write the code after I called malloc, I can have these addresses in line with the code, and that's what LT SPICE does. It's just an example of you have to feel it's real important to have the world's fastest SPICE to write your own assembler and linker and all this stuff. That's what it does. I promise I go fast. I'm not going fast enough on this. You know what? That's enough. You can read the paper. And we'll leave it at that. I always try to go through that fast, but I get wrapped up in it. We're just going to... Done, all right? We good? You guys didn't come here about numerical methods, right? Are we good? Am I making you happy with this? Very good. I see a bunch of happy penguins, so I'm good guy. Yeah. You're all smart. Okay, good. Okay. What I want to talk about now is models. First, I'm going to basically, and this it reads on how to use third-party models in LTSpice. There's basically three possibilities. It's either a power MOSFET model, or the model is done as a native circuit element, or the model is implemented with a sub-circuit. There's three different methods that use. Now, for power MOSFETs, the answer is you don't import it. You use a MOSFET model that's in LTSpice, because LTSpice has a native circuit element that actually behaves like a power MOSFET. SPICE programs don't have that. SPICE programs were for IC design, which are lateral devices, because you can lithograph them onto an integrated circuit. But a power MOSFET is a vertical device, and as a vertical device, you can't print it on an integrated circuit, and it has entirely different Miller capacitance behavior. You cannot use the device equations for a lateral MOSFET pervert. Here's the description of how it works. This is the cross-section of a monolithic MOSFET. Source, gate, and drain are all lithographed on the same side of the silicon. The channel is this region. The channel is defined by the polysilicon of the gate. The length of the channel is the distance from there to there. That's the length of the channel. And the width of the channel will be the direction into the screen. Okay? If you've seen one MOSFET, if you've seen one monolithic MOSFET, you've seen them all. The only difference would be their mechanical dimensions. Okay? Now, if you want to make a high gain MOSFET, something where the same size change in gate source voltage gives you a bigger change in drain source current, the only thing you can do is make it very wide. That's it. You just print it. You run a whole bunch of it in parallel, which means printing it wider. So, if you're making an op amp with the input differential pair and you want a lot of transconductance in that input differential pair, input MOSFETs might be a channel length of 1 micron. It might be a channel width of 100 microns or a millimeter, whatever will fit on the die. Now, if you want to make a power MOSFET, something where a change in 1 volt gate source voltage will give you a change of decades of amps difference in drain source current, then the practical dimensions of that MOSFET is a MOSFET with a channel length that might be half a micron and a channel width of 10 meters. That when you take a power MOSFET and solder it to your PC board, it's a 10-meter wide transistor. See, that's a small area. Half a micron by 10 meters. It's a small area. You could put that in a few millimeter square die, and you could put 6 of them inside of a TO220 package, and they'd rattle around. But you're really dealing with a transistor that's 10 meters wide and half a micron long. Now that channel is rearranged in order to fit that transistor, in order to fit that channel on a die. The electrodes are rearranged. They look like this. This gate is an array of islands of polysilicon. It's an archipelago of the gate polysilicon. Okay, the channel is this region here. This is channel region, and that is channel region. So the width, and then there's many of these polysilicon gates over the whole die. So the width of this transistor would be the perimeter of one island times the number of islands, and that could be 10 meters even on a fairly small structure. Okay, now the source is one massive metallization, just covers the whole side of the whole thing. Now you could put the drain on the same side of the die as the gate to the source. That is a normal thing to do. That's actually easier to do. But if you were to put the drain on the same side of the die as the gate and the source, then you would have to remove so much source metallization so as to appreciably increase the on resistance of the MOSFET. And so the drain is on the back of the die. And that's what the V is about in VDMOS. V stands for vertical current through the die. Okay? Now, D stands for double diffuse, because there's a process schedule you have to go through in order to get the drain electrically on the back of the die. But that's your power transistor, and that's your monolithic MOSFET. You can't use the device equations of this to describe that. But you can for the DC static curve tracing. That's all fine. You can use the same equations for this as you do for that because the channel is so small, it can't have a personality. And you can use the same equations for both. I mean, the only difference is a matter of scale. Instead of microamps on the vertical axis, it'll be decades of amps on the vertical axis. But otherwise, that's all fine. The difference is, well, this has a body diode, this is a substrate diode. The difference is there's this body diode over here to the side. There's no substrate, but it has a body diode here. But that's not really the issue. I mean, you know, you probably don't want to put current through your body diode. You can, but you know, usually you don't. So that's not the big issue. The big difference is the Miller capacitance. There's dramatic a difference between these two structures. I think I had too many of those chicken pies, you know, I have to, excuse me. Okay, now the Miller capacitance is the capacitance between the gate and the drain. And it's due to electric field lines through here, and these electric field lines don't particularly bend independent of whether the channel is conductive or not. So this structure has the same gate drain capacitance independent of whether the transistor is on or off. That's not the deal over here. See, the channel is in between the gate and the drain, and so if you turn the gate on, it's like that dielectric isn't there. You've moved the gate and drain parallel plate capacitance all closer together. Now here it looks like it might just be a little detail, but no, this is all basically conducting, so basically all of the dielectric between the gate and the drain is due to the channel when it's off. The gate drain capacitance changes by about a factor of 3 to 5, depending on whether the transistor is on or off. That's a huge change in Miller capacitance, and since it is the Miller capacitance that determines the switching characteristics of this transistor, you can't use these device equations to describe the behavior of that. That's the problem. At Analog Devices, we developed new device equations that encapsulates a new charge model for a vertical MOSFET. That's what's in LTSpice. If you want to use a simulator with a power MOSFET, just use the native circuit element. The third-party models cannot possibly switch correctly. The third-party MOSFET vendors, they have good intentions. They're doing the best they can. They're making models that will simulate it in any SPICE program, but they just they aren't actually particularly useful. And actually, most of the MOSFET models in LTSpice are actually from the vendor. They send them to me. All right, so that's the deal with power MOSFETs. Oh, let me show you the behavior of this. If you look at a this is the way the gate charge plot. If you ever looked at it, how many people here have looked at the data sheet of a power MOSFET? A few people. Well, they give you a plot that looks like this. It's a plot of gate voltage versus the charge on the gate. And the way it's extracted is a circuit like this. You put a constant current into the gate, so time is the charge on the gate, and they show it while it's switching. What's happening here is the gate, see the source is at ground, so this is gate voltage, but it's actually the gate source voltage because the gate is at ground. You start with the transistor off, you put a constant current into the gate, you charge up the gate. This slope corresponds to a capacitance. At this point, you've hit the threshold voltage, and the drain starts slewing negative to gobble up the charge. The drain will just go to whatever voltage is necessary to gobble up the charge you put on the gate until the drain hits the negative rail. Then it can't slew anymore. It can't Miller multiply that capacitance. And now if you put more charge in the gate, you get this slope. And the fact that this slope is different than that slope is due to the fact, see this slope is different than that slope, is due to the fact that the gate drain capacitance has changed. Now I can draw the drain voltage here. There's a drain voltage. So anyway, now if you ever want to simulate a MOSFET that's not in LTSpice, that's okay. You can do it right away. Just use the assisted mode when you edit the MOSFET. Right-click on the body of the MOSFET, press Pick New MOSFET, and when you sort on the selection guide information, it remembers the order in which you've clicked on them. So first click on gate charge, then click on RDS-on, find one with a similar RDS-on and similar gate charge. Simulate with that. You'll get whether or not you can drive that gate, that MOSFET with that controller or not. You'll get and then use whatever source you want for the MOSFET. So that's how it is with power MOSFETs. The VDMOS transistor has some good general behavior. There were certain, it's a very computationally lightweight MOSFET, but the actual IV curves are more correct than, say, than MOS 1, 2, or 3, or a number of other things. It has subthreshold conduction, and it has actually MOS 1, 2, and 3 of Berkeley Spice. There was a mistake in the Singh-Shinhad's derivation, and so these equations, these IV curves are actually quite different. They will that's what you want. This power MOSFET will work for any vertical MOSFET. If you want to make a hi-fi stereo amplifier, this is the MOSFET model you use. These are the device equations you should use. These will be accurate. Okay. Now, people often want to use third-party models in LT-SPICE, and so I will like to show you how to do that. A model is basically a text file. And you have to look at that text file to see how to include it. The text file has to be either a native subcircuit, a native circuit element, or a subcircuit. If it's a native circuit element, it's implemented with .model statements. The idea, like take this part here. There's no, if you want to use this third-party model in LT-SPICE, it's a common diode. You just include the model. I put it as text as a SPICE directive on the schematic, but you could put it anywhere. And put it in a diode instance with the value of the diode coinciding with the name of the model. And then that's running that model. Basically, because it's the native circuit element, the guy who authored this model, he said, look, I know SPICE knows about diode IV curves. All I have to do is parameterize the built-in equations to match my product, and I've made a model for my diode. That's what's going on. It's fairly simple. And this really is the easy case. The reason why I show it is to differentiate it from the next thing I'm going to show you, because here you already have a symbol. The symbol pinout's all correct. You just have to include it. In fact, the GUI will help you deal with this thing. You could put this model file in the model diode database so that when you right-click on the diode and press Pick New Diode, it would show up in this list. This is the easy situation. Now, where people get confused is with subcircuits. People have a lot of trouble with subcircuits, and the problem is you don't have a symbol, it's hard to get it connected into the simulation correctly. Now, most engineers, after you've been doing electrical engineering for a while, you get familiar with netlists because you have to verify a layout against the schematic, and people get familiar with netlists. And then they, because LT-SPICE is a physical simulator, there should be an analogous process to using a third-party model in a simulator as there is from using an actual, a sample from a vendor. And what's that process? You get the sample from the vendor, you have to read the data sheet to find the pinout, and then you get it connected in your circuit, and you go forth from that. There should be an analogous process. So they figure, okay, I'm going to be okay with this. I got the ASCII file of the subcircuit. It's like a netlist, and I understand netlists. I should be good. They're ready to go. And then they make a mistake. What they do is they read the help file. Don't do that. Okay, now it's not that the help file isn't correct. It's not that it isn't thorough. It's not that it's complete. It's not that it hasn't stood up to millions of readers. Problem is, there are times in our life where we're better off if we just accept what we are for a species. All right? I mean, what are we as a species? We do not read the words on the paper. We read the words that we're thinking in our head. That's just what we are, okay? And, when you try to get these subcircuit hooked up to the symbol, people don't keep straight that the actual number 3 and the string of Arabic numeral 3, or Latinized Arabic numeral 3. If you know Arabic, I don't know. I go to Arabic countries too. Anyway, and the pin called 3, the SPICE order, those are all different 3s. And people just read what they're thinking in their heads. So look, don't read the help file. Let me show you the one and only way you should ever consider using a third-party model in LT-SPICE. I have, at great consideration and meditation made this as simple as possible to do. So I'm going to show you exactly how to use this. I do not know how to make it easier to use a third-party model. Three-step process. You only really have to remember the first step. And the first step is open the file in LTSpice. LTSpice has a text editor, you know. It could show you this, even colorized spice syntax. See, comments are in green, dot commands are blue, normal not less than back. So step one, that's the only one you really have to remember, is open the file in LTSpice. Good. Step two, point at the line that says dot subcircuit. Now in text editors, there's two different ways of pointing. One is with this little blinky blinky, and the other is with the mouse cursor, okay? Don't worry about the blinky blinky. Just point at it with the mouse cursor. Okay, that is step two. Point at the line that says dot subcircuit with the mouse cursor. Then, step three, final step, right click, create symbol. And there it is. Okay, now I realize it's just a square box. Okay? But the value of this is that these pins netlist against those ports. It just does that for you. Now it will show you the thing in the graphical symbol editor in case you want to rearrange pins or change its shape or whatever, you know. But you don't have to do that. You can just leave it as it is. It works right now. So it shows you the symbol, and these pins will netlist against these ports. But that's not the real magic. The real magic is this symbol is now programmed to include this file whenever that symbol is on a schematic. That's the magic. And that's why step one was so important. When you open the file in LTSpice, it knows the path, so it can write that program. Okay, that's the magic. Now so let me just say, let me make this clear so you don't forget how to do this. A lot of times I'll give a talk, I'll show how to use third-party models in LTSpice, and then a day or two later, I'll get an email from the attendee and say, okay, Mike, I got all these third-party models I want to run in LTSpice. I'm not going to tell you where I got them. And I went to your seminar, and I'm not going to read the help file. And now I want to know which directory I should put these in. It's going to be okay. You should have a quiet moment and reflect on where you would like those files on your hard disk. And at the end of that moment, that's where you put them, okay? And then because step one is open the file in LTSpice, you share with LTSpice your, divine preponderance is where they should be, okay? That's how it works. That's all there is to it. I really don't know how to make it easier. Remember, step one is open the file in LTSpice. It's the only one you really have to remember. And as soon as you have it in there, you can drop the schematic and run the thing. In fact, people are, well, where will the file be? Well, they'll be in the symbol browser. Press F2, the symbols are organized in directories. There's a directory called auto-generated. The significance of the name auto-generated is that it starts with the letter A, so it's near the top of the list, and you can find it. You go in there, and that's your symbol. Okay, great. And this was an op amp, and here you can see I can run the simulation, you see a clip. That's the good news. The bad news is it's actually very unlikely you find a good SPICE model. It's just exceedingly unlikely. The SPICE models are actually made by the company that makes the products, and most people that make the products, they neither have the, they don't have the expertise and to make a good model, and they just have a hard time seeing why they should make a model. For them, they're going to hide behind an argument that goes like, well, we're a hardware company. We worry about the hardware. We're not worried about some computer file that goes in some software you got from somebody else. That's not what we're about. It's just whatever. But it's just exceedingly unlikely to find a good SPICE model. Now, that's the reason why it comes out. That's the psychology of why it's extremely unlikely you find a good SPICE model. But let's put this on now an actual technical basis of what's wrong with SPICE models. And let's talk about op amps, okay? Because it's really a reasonable expectation for you to think that you can get an op-amp model, put it in a SPICE program, and get reasonable results. It's a really reasonable expectation because it's an analog product from an analog company. The product was designed in the very simulator you're using this. I don't know how to make it. It should work. I mean, it's really a reasonable expectation. It's amazing that it doesn't work. And the real reason why it doesn't work is that actually SPICE is an incredibly bad programming language to describe op-amp behavior. I mean, it does pretty good with transistors, but the person who made the op-amp went through great lengths so that you don't see transistor behavior in this op-amp. You just see idealized or nearly idealized behavior. And SPICE is a really bad programming language for describing that almost ideal op-amp behavior. Now, to solve this problem, there was a gentleman by the name of Boyle, and he advocated methodology on how to make an op-amp. He had good intentions, but his papers on modeling op-amps is one of the biggest disservices to the electronics industry ever. There is nothing particularly correct about the Boyle model. For example, if you look at the pin currents about a Boyle model implemented op-amp, you can, objectively, you can fairly come to the conclusion that the Boyle model feels that Kirchhoff's law, it's just a recommendation. Okay, that's the problem. Now let me, and the company I used to work for used to distribute Boyle model. Let's talk about the LT1001. That was actually, I came into analog devices with linear technology, and that was linear technology's very first op-amp. You can still buy this thing. It was designed like 30 years ago, and you can still buy them. And okay. Now I have both. I'm going to run the Boyle model compared to the LT SPICE version. All right, let's look at pin currents. This is the positive supply pin current and negative supply pin current. This data says there's 1.6 milliamps positive supply pin current and minus 1.6 milliamps negative supply pin current. Again, pin current sign convention is positive into the pin, so that data is telling you that there's 1.6 milliamps draw through the positive supply and going up the negative supply pin. Good. So you look at the output current, 10 milliamps. Now, it might not cause much reaction to you sitting here, but if you were on a bench and you saw an op-amp behave like this, I would wager that would cause a reaction in you. All right, that if you have a part, you put 10 milliamps, you put 1.6 milliamps in and get 10 milliamps out. In fact, I think this is a big enough thing that it's moments like these that you can really differentiate a person's character by the type of reaction they have to this. Really, I'm dead serious. Look. Okay, like one person would look, let's see, I put 1.6 milliamps in, 10 milliamps out. This is amazing. I'm going to write a paper and I'm going to be famous. Well, that person is motivated by fame. All right, that's what he's about. Okay, as a human being, that's what he's motivated by. That's what he's doing. Another person would look at, let's see, I put 1.6 milliamps in, 10 milliamps out. This is amazing. I'm going to patent this and I'm going to be rich. I mean, he's just motivated by money, okay? I mean, you can really, these are the moments that differentiate, one person's character from another, okay? Another person would look at this and say, let's see, 1.6 milliamps in, 2, 4, 6, 8, 10 milliamps out at voltage. This thing is emitting energy. We're going to make fields of these parts, we'll harvest the energy, we'll solve all the problems on the planet, and we'll have world peace. Well, he's just a people pleaser. Okay, there's no depth of character there. I mean, there's nothing there. He's just a people pleaser, all right? Now, I will tell you something. If I saw an op-amp behave like this, it would cause a reaction in me, okay? And I'd like to think that I would recognize that this is bigger than wealth or fame. This is bigger than world peace. It is. Because if I saw an op-amp behave like that, I would immediately disconnect my association with technology. And I would spend the rest of my life feverishly studying religion. That is a miracle. There's no other way of looking at it. Okay, that's what I would do. Now, if you try this at home, it's not so exciting. Okay, because if you try an LT Spice op-amp model, positive supply pin current, negative supply pin current, it's just going to steer current above the pins. It's boring. You know, and you know it's going to have the right small signal response, the right drive capability response. We do as we can, as best we can on the output impedance, so we overshoot into a capacitive load will be about right. We'll model the input capacitance as normal mode and common mode. So if you use the high impedance feedback network, the extra pole to the input capacitance, that'll all be modeled both modes. Input common mode range, it just works like the op-amp. It's actually boring. Okay, so that's the deal. And we also do this with op-amp circuits that have only, you know, 7 to 10 nodes inside of them. The speed of a simulation model depends on the number of independent voltages. You know, this will only have a few independent nodes, and that'll probably have 40 nodes internally. So it'll simulate about 10 times faster, and it'll actually work like an op-amp. That's what we've done. Now, that's one problem with the Boyle model. Another disappointment for the Boyle model for me is the way it handles stochastic noise. And for that, I'll talk about this part here, because this part has changed my life, the LT1028. I used to make instrumentation used in explorative oil drilling. Now, the way you find oil is by rock resistivity, because after you go down about 300 meters, it's all salt water. It's all conductive. But wherever there's oil, the salt doesn't dissolve in oil, and that's high resistivity. And it's through formation resistivity, that's how the oil is found. And it's the only way oil is found, and it's the only way oil has been found for all 70 years of heavy oil exploration. My job was to make the preamplifier. By the way, when you measure the rock resistivity, you do it inductively, because around the borehole, you've invaded the borehole with conductive stuff because of the process of drilling, so you have to measure the rock through, you know, a few feet away from the borehole. That's done with antenna coils. You know, you set up eddy currents and you measure that. And my job was making preamplifiers for these antenna. Okay. Now, because of the LT1028, I was doing that in the mid-'80s. The LT1028 was released in the early '80s, and it was the lowest voltage noise op-amp available. Its equivalent input noise density is typically 0.85 nanovolt per root hertz. Order of magnitude quieter than any other op-amp, and even to this date, it's still the lowest voltage noise op-amp available. This part changed my life. Actually, I heard of, before I worked at the company I work at now, it's because of that part. Okay, so let's talk about the noise behavior of this. So let's look at this circuit. We have a 10 ohm resistor, and then here a 10K resistor. The voltage gain of the stage will be 1,000. And then because that's 10 ohms connected to the inverting input, the non-inverting input is connected to a voltage source which has no impedance. What this means is the voltage noise will be amplified by a factor of 1,000, and the current noise will be shorted out. The significance of this circuit is that it is a voltage noise test fixture. All right, now what noise should we get? 0.85 nanovolt per root hertz times 1,000 will be 0.85 microvolt per root hertz. This resistive network will have some Johnson noise and add in. The correct answer is that you should have a microvolt per root hertz on the output of this op-amp. And let's compare this to the Boyle version compared to the LT Spice version of the op-amp. Okay, so in the Boyle model, we're expecting a microvolt, but we're getting over a millivolt. Okay, and that's just sad. You know, that the lowest voltage noise op-amp commercially available has its noise incorrectly modeled by more than 60 dB. Okay, but if you look at the LT Spice model, you see we're expecting a microvolt, and that's what we're getting, a microvolt. This 1 over F performance here, that is the 1 over F noise of an LT1028. Its corner frequency is here at 3 hertz. That is the noise you get. Now, what about all this structure up here at high frequencies? What about here? At real high frequencies, you don't see any noise. And there's certainly noise out of an LT1028 at 10 megahertz. That's all true. But there isn't, an LT1028 doesn't have a gain of 1,000 at 10 megahertz. So the voltage noise test fixture doesn't work at that frequency. It's just that this circuit can't test the noise there, and that's why. This is the correct simulation result. It's just you can't see this. Then there's this little mountain of noise here. What's up with that? Well, that's because the input differential stage of the LT1028 is so quiet that subsequent stages, it's so quiet that when it amplifies the signal, the subsequent stages add noise, and this amplified noise from the input hasn't swapped the noise from every other stage. And you will see the noise from those intermediate stages when the open loop when the feedback loop goes open circuit because of loss of gain bandwidth. So, see, basically, you can think of this intermediate noise as a voltage source in series with the output. If you put a voltage source series here, it will be, this point will be servo, because you're sensing, this point is looking at that thing past that internal noise source, and if you have enough feedback, negative feedback, you'll servo out any noise that's in series with that output. But the feedback loop is going open circuit, and that's where you see that noise. What I'm saying is it's an exact noise model. Now let me tell you the noise contributions that are included in LT Spice op-amp models. There is voltage noise density and current noise density, and voltage noise and current noise density over frequency. And we don't just model these voltage noise densities over frequency, we model these noises over bias conditions, because the noise of an op-amp depends on how it is biased. Let me give an example on how that happens. Consider a rail-to-rail input op-amp. Now in op-amps, when you hear rail-to-rail op-amp, usually that's probably just rail-to-rail output, okay? And, but if you have a rail-to-rail input op-amp, the way they're implemented is two different input stages. So you consider here an N stage. These plus and minuses will be the rails. All right, here's the input. Now the common mode range of this will go to the positive rail, maybe even a little above, but it won't go to the negative rail because this current source needs some voltage headroom to keep behaving like a current because it's some active circuit with semiconductors. So this will go to the common positive rail, but not the negative rail. So to make a rail-to-rail op-amp, you have two input stages. One is N polarity, and the other is P polarity. Because this stage will go common mode to the negative rail, but it can't work to the positive rail because this current source needs voltage headroom. And then you have circuitry to switch between input stages depending on the common mode current. And that's our op-amp, okay? Anyway, these diff pairs have different noise characteristics, and our models will look at how it's been biased to say which noise it should report. But there's more. We don't just model input voltage and current noise densities over frequency and bias condition. We model the noise from these tail current sources because they have a noise contribution that is not included in input common mode current. Common mode current is basically a normal mode current that's read out against the impedance between these two. If you have the easy example to let's do this for a let's consider a JFET input op-amp. This is maybe where it's most popularly understood. Say that's the differential input pair of a JFET input op-amp. Well, this current source here, if there's the noise on this current source is coupled to the inputs, you know, say capacitively, and then that makes a common mode current going out the inputs, which will be read out to a voltage by the impedances seen on those inputs. Okay? So this common mode current is read out to voltage with these things. Now, if you have a situation where Z1 equals Z2, then this common mode current is read out as a common mode voltage, and it's rejected because the high common mode rejection ratio of the op amp. That's all good. But if Z1 is not equal to Z2, which is probably why you're using an op amp in the first place, then this common mode current is mode mixed to a normal mode signal, which is on the input and it's amplified with the full gain of the op amp. And we include that too. So we basically we did the same, in the LT Spice group, we did the same thing to op amps that we did for switch mode power supplies. When I started working at LT Spice 20 years ago, we just, to model these products so that you could simulate these switch mode power supply products quickly, we just did whatever was necessary to the simulator to make it possible to author very fast switch mode power supply controller models that were accurate and you could simulate them interactively. And so we defined the state of the art of switch mode power supply simulations. We had that nailed about 15 years ago. Okay, we just owned that field. Then about 6 years ago, we just did the same thing to op amps. We just implemented in the simulator whatever was necessary to make it possible to make a computationally lightweight op amp model that would be accurate and have exact noise models. And we re-authored every single op amp model that we had with this new methodology. So we also defined the state of the art of op amp modeling. Okay. That's what I wanted to say about third-party models. Now let's see. I was supposed to end at 4, and it's 20 after 4. We have choices here. We can retire to the lounge and drink cognac, smoke cigars, and slap each other on our backs and say how we conquered the world, you know. Or we can do one more little thing that's maybe fun. I don't know. You guys might not enjoy the fun thing because it kind of deals with kind of old, gristly analog engineering people. They find it very funny. I don't know if this goes, but what do you want to do? Call it quits? Or maybe it's one thing that might be fun. This is like a funky old uncle saying, "Oh, I got something funny for you." You know, this might not be good for you. I don't know. Okay, so I really can't suggest which way to go on this. Are you guys happy? You guys done? Happy done? Oh, I know what we're going to do. We're going to have Q&A. We've lost the remote sites, so this would be a very intimate, quiet Q&A here, you know. This is going to be a fun little Q&A, you know. How many cigars did you bring? Did you bring enough cognac for everybody? Yeah, all right. It's that email. Maybe I didn't get out there. Okay. All right. Let me tell you a few things then, just before we go into. Oh, that's weird. That's not the right. That didn't work. Okay, forget that. Oh, I know what the problem is. Never mind. I really appreciate you folks listening to me today. If nothing else, you probably at this point realize that LT Spice is the only thing I do for a living. And that means that your interest in LT Spice is as close to a matter of life and death for me as I care to get with a bunch of strangers, okay? There's no other way of looking at that. Now, if you did like the seminar today, you can thank the local ADI presence, Mr. Sherman here, you know, your gratitude for, and that's all I've got. Thank you much.
questions? Let's give a round of applause to Mike.
All righty.
So one last request before we leave, can we take like a last picture in front? So we can. Nice. You might.
All right, sir.
Then I think some guys can go here and then you guys back.